All right, so let's go over a few questions, okay? The more that we do, the less you have homework. But one point I want to make before I'm done with today is that this thing called enthalpy, okay, delta H, or heat of reaction, okay, has been given a definition for you guys to understand. And you can certainly memorize this, but I'd rather you totally understand it. So delta H, as we have learned, is the difference where we start and finish. If I look at this curve, what's the first thing I ask you to do when you look at this curve? See where you start and finish. Am I going up or am I going down? Overall, I'm going up in energy. So it's clearly, in order to finish with more energy than I started with, energy had to come in, it's endothermic. I'm climbing the ladder. You go upstairs in your house, you need energy to go up. My products have more energy, potential energy, than my reactants. This is endothermic. It's the first thing you do. Now, what's the value of the sign? Should it be positive or negative? Positive to show that the difference of where I start and where I finish is going up. Now, in order to use that positive and negative idea really well, they came up with a convention, a way to make this work. And here, how do I get positives? Let's pretend that this is 10. Let's pretend this is 20. So we'll put a 10 here. I'll put it there. We're just making some numbers up. Make this 10 and make this 20 kilojoules. What would be the value of delta H? The difference of where I start and where I finish. What's the change in overall energy? What represents the energy that needed to be absorbed in this reaction? What's the value? Plus 10. Positive tells me we're going up. We started here, we're going up. So by convention, you will see this as a choice. What's the definition of delta H? And you will see it written as delta H is equal to the potential energy of my products minus the potential energy of my reactants. Why will it be products minus reactants? That's the only way I can get what kind of value in this case. A positive one. 20 minus 10 gives me positive 10. So it's always products minus reactants because that's going to give me the sign I need. I want a positive sign. I want to say that it's going up. Delta H is positive 10 in this case. What does that mean? It means it's going up. Okay, let's change. It's going up 10. Up 10. So delta H is equal to positive 10. The only way to get positive 10 is products minus reactants. What about the reverse reaction? What's the value of delta H now? Negative 10. So if it's negative 10, if I go in the reverse, this is now my products. 10 minus 20 gives me negative 10. So it's always products minus reactants. That's the way that we get the sign that makes sense of the movement of change of energy. Okay, let's go over some questions. Which letters in the diagram represent the potential energy of the products? Oops, not that. What's the potential energy of the products?
Wouldn't it be A and E?
Where are my products? Is Z a product or is X and Y products? Z is a product. X and Y are reactants. We always start with our reactants, right? What did I put in my vessel? I put in alcohol, and oxygen was already in there. It's what I start with. We always read left to right unless told otherwise. So this is my products. So what's the potential, what's the energy of the products? How much energy does the products have? E. It's right, it's 20, but it's E, it's letter E. Or E. Number 2, which letter indicates the potential energy of the activated complex? That activated complex is the highest energy position Okay, and it represents the total energy. So C. Or yes, I mean C. 3, which letter indicates the potential energy of the reactants? I start here, I finish here. These are my reactants. How much energy do I have? Is this easy? Who is the activation energy? Notice it didn't say reverse or forward. What would be the activation energy? What energy is needed to get over the hump, to start the reaction, to climb the slide? Well, D would be the activation energy of the reverse. Hey. B would be the energy needed to start the reaction in the forward. Now, they didn't say reverse or forward. Because they didn't say reverse, you basically have to assume they mean the forward. So B is the activation energy of the forward. They didn't say the reverse, so we do that. Which letter indicates the heat of reaction? Heat of reaction, the delta H, the enthalpy, the difference of where I start and I finish. F is the difference of where I start and finish. I don't want to F around anymore. So F. Where am I? Over here. Is a reaction exo or endo? Am I going up or down overall? Up because I'm absorbing energy, so therefore it is endo. What's happening to the temperature of the environment? It's going down, right. Who's the activation energy of the reverse reaction? Duh. In the reverse, you start here, you go this way. The energy I need to start the reaction is letter D. Oops. Which letter indicates the heat of reaction of the reverse reaction? Heat of reaction, fancy word for enthalpy. Well, the forward reaction is F. The reverse reaction is still going to be F. That value doesn't change. The sign changes, but the amount doesn't. So it's F again. All right? Oops. That's F. Is the reverse reaction exo or endo? Well, if the forward is endo, the reverse is exo. Now, if a catalyst were added, ooh, catalyst, that's medication. Let's add it. Add some medication. What's it do to my pimple? It's going to lower it. I'm going to medicate that bump. Maybe it's a wart. I don't know.
Ew.
What? Okay? I'm going to medicate it. But you notice I'm not changing where I start, where I finish. I'm just changing the pathway. So the question reads what? If I were to medicate this hump, okay, if a catalyst were added, which leaded quantities, if any, would change? D would definitely go down. Who else would go down? C would go down, and B. So, fucked up. B, C, D. I've got problems. I understand. B, C, D. I'm not sure if I actually said a bad word there. Okay. Would the activation energy be increased, decreased, or remain unchanged? So if I was to medicate this.
Too bad it wasn't F.
Yeah, I wouldn't have said it. All right. Now, if there was a catalyst added, what happens to the activation energy? They decrease. Okay? Maybe I would have. I don't know. Decrease. Go down. What would happen to the heat of reaction? Put a big decagon around this, 10 sides. No, just kidding. Put a circle around this. Yeah. How do I do that? This is an important question. By medicating this hump, yeah, medicating it, do I change where I start and where I finish? Does a catalyst affect delta H? The answer is no. So the answer is unchanged. Delta H, and mark my word, if you can mark it. Okay? People will get this wrong. Delta H does not change with a catalyst. How much heat's released or absorbed, the difference between start and finish does not change. Okay, flip it over 9 times.
What?
You didn't count right. Okay, after you flip it over 9 times, if that didn't work for you, try 27 times. Okay, I'll make change for you later. After class, I'll make change. Okay. Now we have numbers. Oh my gosh, numbers! Is this reaction exo or endo? Don't yell it out. Telepathically tell me. Don't yell it out. I'm telepathic. Sorry. Okay, you should be ready. You are right. So clearly it's exothermic. Why is it exo? It's going down, yeah. You start with this much energy, you got lower because you released it. What's the value of delta H? Negative 30. You got to put the negative. You forget it's going down 30. I have to mark it wrong. Negative 30. Now in this case we're using kilocalories, but I like this ditto. Negative 30 kcals. Right? You're at 40. What's delta H? Products, 10, minus the reactants, 40. 10 minus 40, negative 30. What's the value of the activation energy? Must be the forward. Activation energy. The energy needed to do what? Start the reaction. Get us over the hump so I can ride the slide. Ride the slide. I'm the top to ride the slide. How much energy do I need? 20. Or svansek. Say svansek. 20. 20 kcals. 4. What's the potential energy of the products? What if I eat the product?
You're a little above it. You have to go below. Go down.
All right. 10. The product's energy. What's the potential energy of the activated complex? The guy that lives on top of the hill. How much?
Wait, we didn't do 4.
4. Potential of the products. 10. I speak softly. So that's 10. Potential energy of the activated complex. The maximum energy you have to overcome. 60. That was tough. Take a break. Break's over. Okay, next one. Almost done. I'm not going to do any more, except for the ones I do. Okay? Okay, next question. Is this reaction exo or endo? Don't scream it out. Telepathic answers, please. Jordan, what would you say that about? I wish I could do that. I'll try. I'm glad I pulled some out. I can't afford to do that. Why is that funny? All right. Is it exo or endo? Starts with an E, Cameron. What do you think, Cameron? Endo, because we need more energy. We're making a bomb. We're making energy. We're storing energy, going low to go to high. So endo. That means it's taking in energy from its environment. Okay, what's the value of the active? Now this gets crazy now. What's the value of the activation energy of the uncatalyzed? Uncatalyzed, unmedicated. Uncatalyzed, unmedicated. So I want the activation energy, which would be what? The energy that I need to climb the slide, but I'm unmedicated, so that sucker's big. All right? 25, okay? What's the value of the activation energy of the catalyzed reaction? Now, catalyst means medicated. Ooh, I've calmed it down. Okay? So now it's 20. It's that simple. People just yelling out answers like, this is just a joke. 20 kcals, I should put. But what's the potential energy of the activated complex of the catalyzed? Medicated. The activated complex is that highest energy peak. It's now catalyzed, so it's medicated. 30 is right. How does a delta H for the catalyzed reaction compare to the uncatalyzed, unmedicated? We have greater. Anyone agree? Yeah, the difference of where you start and you finish does not change if you change the pathway. Right? So it's the same. Okay. Now, the last bit of this worksheet, okay, is pretty straightforward, except what makes it hard is the lines are all pushed over. Like if I wanted, and this is part of your homework, if I wanted to know the potential of the activation energy of the forward direction, I know it's from here to the top of the hill. So I gotta go find that line. What would it be? Right. Good. If I wanted the reverse activation energy, again, unmedicated. Reverse activation energy. Good. All right. What if I wanted the medicated, uncatalyzed, unmedicated, right? Unmedicated, uncatalyzed, reverse activation energy. Unmedicated. Okay, so that's part of your work at home. Okay. Now, 5 more minutes and we're going to start a lab. Okay. Introducing for the first time, or maybe the second time, Table I. Okay, well, not quite. Table I. Now, Table I, okay, has some reactions, and notice, party people, it has delta H's. The first third of Table I are combustion reactions. I have a fuel plus oxygen gives me CO2 and water. In fact, anyone notice this reaction? Okay, that's our reaction we had today, ethanol. Okay, and look at the delta H. What's the value of delta H? What's that little thing in front? Negative, which means it's exo or endo. Exo. So we have this chart that tells if things are exo or endo. In fact, if you don't like that, what's nice, and you can use this to your advantage, at the bottom of Table I, okay, if I can throw it up here, it says this. The values are based on molar quantities represented in the equations. A minus sign indicates an exothermic reaction. Okay? So in today's lab, we're going to use the bottom third of this table. Okay, if I can do it. Maybe not. There we go. Let me go around. Okay, bottom third of this table, which are ionization reactions. Now, what does it mean? It means this, party people. When these salts, hey, ionic compounds, hey, electrolytes, hey, break apart into their ions in water. Sometimes they're endothermic, sometimes they're exothermic. We have 2 salts in lab today. One is going to make the temperature go up, one is going to make the temperature go down. Which one is which? Okay, now I'm looking for something that I can't find. Here it is. Kind of gross? No. Here we go. It's called a hot pack. Okay? Now hot packs, if you ever got one from the nurse, you press the water, you press a little bag in the inside, and you burst a little water. In fact, a hot pack looks like this. Okay? It's got a big pack on the inside, on the outside. And let's just do this. File new. Now let's go here. File new. So a hot pack has a bag like I've showed you. It's sealed, and inside the sealed bag there are salt particles. And then inside this bag there's another bag filled with water. If you ever dealt with a hot pack like this way, you burst the bag inside and you shake. When you shake, you're mixing the water with the salt. Now if it's a hot pack, making the environment warmer, is the salt, when it dissolves in water, going to be exothermic or endothermic? Exothermic, sodium hydroxide could be that salt. Lithium bromide could be that salt. But if you want a cold pack, and I've opened these up, so here's this cold pack. It's got this salt in it, and it's got this water bag. So in those packets, you've got a water bag that you burst, and you mix it with this salt. Now this is a cold pack. It's going to make the environment colder by taking the energy in. What kind of delta H would I have if it's a cold pack? It takes the energy in. It'd be positive, you're going up. So ammonium nitrate could be, in fact that's what it is. Ammonium nitrate's used. And it makes it cold because it takes energy and consumes it from the environment to store it into the products. And what would the curve look like? What would your curve look like? Curve would do what? Your curve would start low and go high. And the reason why it takes energy in, it needs energy in its environment to go into the products. Okay? All right. So you're finishing that first worksheet that we worked mostly out together. The second one that I gave you is also due, and I have a lecture that walks you through that. Take out your lab.